Hello, howdy. This is Limits Lesson 2B, Limits Involving Infinity. This is the second part of Topic 2, which focuses on vertical asymptotes and end behavior models. At the end, I'll wrap it up with some tips about how to see difficult limits. Here we go. We'll start with vertical asymptotes, and we'll use these two functions to help define a vertical asymptote in terms of a limit. The informal definition of a vertical asymptote is a vertical line that a function approaches. Notice that the function 1 over x approaches the vertical line x equals 0. Wonderful. We found that asymptote using a graph, but what does that have to do with limits? Well, before we even look at the graph of the function 1 over x, we should know that there's an issue when x equals 0. F of 0 is undefined, so let's use limits to figure out what's happening. We can take the limit as x approaches 0 from the left side of 1 over x. Then compare it to the limit as x approaches 0 from the right side of 1 over x. We can use a table or a graph to conclude that the left-hand limit is negative infinity. And the right-hand limit as x approaches 0 from the right side is positive infinity. Since these one-sided limits are infinite at x equals 0, the line x equals 0 is a vertical asymptote of the function. Evaluating a limit is what allows you to formally conclude that a vertical asymptote exists. Let's look at another function, g of x equals tangent x. On the TI-84, I use zoom trig to get this graph, which means that the scale is pi over 2. So we have pi over 2, pi, 3 pi over 2, 2 pi, and so on. Vertical asymptotes for the tangent function happen at every odd pi over 2. So positive or negative, 1 pi over 2, 3 pi over 2, 5 pi over 2, and so on. We'll focus on pi over 2. At x equals pi over 2, it looks like there's a vertical asymptote. So we'll use limits to verify that. The limit as x approaches pi over 2 from the left side of tangent x is equal to, well, shucks, where do I even start? Which part of the curve? I'll start at the far left where x is close to negative 5 pi over 2. I'll follow this leg of the tangent curve. Y approaches infinity, but I'm jumping to the next part of the curve because x is not at pi over 2 yet. I keep going through, here's negative pi over 2, y approaches infinity. Jump to the next part of the curve, and x is getting closer to 0, up the curve. Aha, here we go. X is really close to pi over 2, and y approaches infinity. Now for the right-hand limit. The limit as x approaches pi over 2 from the positive side of tangent x is negative infinity. I'll show you a different way now. I put my pencil at x equals pi over 2, then move it to the right until I find the curve. Then follow that curve in the direction that the limit says. Approach pi over 2 from the right side, therefore we go down the curve. Since the left-hand limit and the right-hand limit are infinite at x equals pi over 2, the line x equals pi over 2 is a vertical asymptote of g of x. So, what conclusion can we make? From these two examples, we might say that if the left-hand limit and the right-hand limit are infinite and opposite at a specific x value, then there's a vertical asymptote at that x value. But the limits don't have to be opposite. Consider the rational function 1 over x squared. The left-hand limit at x equals 0 is positive infinity. The right-hand limit at x equals 0 is positive infinity, and x equals 0 is the vertical asymptote. Now let's switch gears a bit and check out end behavior models. An end behavior model is a function that models another function as x approaches positive or negative infinity. When finding end behavior models for a complicated function, we're trying to figure out if it acts like a common function when x is large. We'll look at two functions, The first one is 2x divided by the square root of x squared plus 1. To find the right end behavior model of this function, we'll take the limit as x approaches positive infinity. When x is very, very large, I'm talking billions, trillions, super huge, that little plus 1 inside the root doesn't matter. So this limit will be equal to the limit as x approaches infinity of 2x divided by the square root of x squared. The square root of x squared is equal to the absolute value of x. So therefore we have the limit as x approaches infinity of 2x divided by absolute value of x. Since x is approaching positive infinity, we have 2x divided by x, which is equal to 2. Thus, y equals 2 is the end behavior model. To find the left end behavior model, we'll take the limit as x approaches negative infinity of this function. And again, we get 2x divided by the absolute value of x. When x is negative, this expression becomes 2x divided by the opposite of x. In other words, plugging in negative numbers for the absolute value of x will result in a positive number. The expression negative x, or the opposite of x, is essentially doing the same thing. The x's divide out, and we end up with negative 2. Therefore, y equals negative 2 is the left end behavior model for this function. This means that when x is a very negative number, the function 2x divided by the square root of x squared plus 1 acts like y equals negative 2. I encourage you to graph the function to verify that these models make sense. The last example of this lesson is to find the end behavior model of x squared minus 2x divided by x plus 1. And I'll show you a slightly different way to do it. We'll take the limit as x approaches positive and negative infinity at the same time of this function. Then we'll separate it at the end. When x is very large, that little plus 1 in the denominator doesn't matter. That little plus 1 is like a grain of sand, whereas infinity plus 1 is like all of the sand that has ever been produced or can ever exist. And you might not like this one, but when x is very large, like positive infinity or negative infinity, that negative 2x is nominal in comparison to x squared. In short, the terms that matter the most in the numerator versus the denominator are the terms with the highest degree. Therefore, we have the limit as x approaches positive or negative infinity of x squared divided by x, which simplifies to the limit as x approaches positive or negative infinity of x. Thus, y equals x is the end behavior model for this function. The function acts like the identity function y equals x when x is very large. Graph it so you can see it. It goes up to the right and down to the left, with some other stuff in between. You may have noticed that the process for finding end behavior models and horizontal asymptotes are similar. Keep that in mind, but notice the difference too. Working with limits can be challenging. They can seem subjective, technical, or nuanced. I think what makes them challenging is that evaluating them or working with them requires analytical skills. If you don't usually pay attention to detail, maybe this is your opportunity to increase your analytical skills, your ability to analyze things. That's why it's helpful to have multiple approaches to evaluate limits. You'll notice in this list that I moved the algebraic approach to number 1. If you can evaluate the limit algebraically, it's the quickest way. If not, then pull out your calculator and look at the table. Make a conclusion, then graph the function to verify what you saw in the table. If you can't find the limit algebraically, numerically, or graphically, then that means you might need to try the sandwich theorem, which is the theorem that I shared in lesson 1b. Finally, there's this new approach. If you're finding the limit as x approaches positive or negative infinity of a function, and you end up with something weird, like something undefined, then try replacing x with 1 over x and change the limit to x approaches 0. The need for this approach would be quite rare in a high school Calculus AB class. But you might come back to it when you study L'Hopital's rule. Sorry, I don't have an example for it. So if you think you might need it, just try it out.